a new feature. We're using a new video interface today. In the upper right-hand corner of your window, there's a small window with a video of the presenter. That's me. And if you'd like to make it larger, just go ahead and use your mouse, grab it in the lower left-hand corner, and just expand it as you would any other window. And you can go ahead and fit it to the size of your screen that's most comfortable for you. So before we get started on today's module, which will be this is a little bit of background on our company, by the way. Oh, also, everybody, if you didn't get them, please call that 877 number. We did email a copy of all the presentation materials for today. The one that starts with 01 is what I'm starting with right now, and it's got a little bit of background information on what the webinar is all about. And then we're going to be doing modules 5A and 5B. You'll see the module number in the lower right-hand corner of the paper when you print it out. Okay, so this webinar series is broken into 12 modules. It's basically our 3-day HAZOP facilitation course, and it's broken into basically 90-minute segments that we don't do breaks. We go ahead and just push you right through it. At the end of it, you should be in pretty good shape for going out there and handling some pretty challenging problems. What we've done so far is talk about regulatory requirements, overview, and do a little case study in Module 1. Module 2 was about HAZOP study mechanics, quality tips, and consequence analysis. Module 3 was focused on preparing for the PHA and getting good quality P&IDs together, and a little bit about those P&IDs. Module 4, which is the last one we did, was on scenario details, and also we did a little workshop in terms of how to construct scenarios that are useful for your HAZOP study. Today we're going to be focusing on facilitation tips, a little bit more background information. That'll be about the first half hour. It'll be mostly me providing some insights and things that work well and don't work well when you're facilitating HAZOP studies. The second half will be focused on quantitative techniques and specifically revolving around something that tends to be a bugaboo for a lot of HAZOP studies, which is dealing with double jeopardy issues. Double jeopardy, we'll go into some definitions, is a commonly used term for things outside HAZOP studies, and it tends to be misapplied a lot for during HAZOP study sessions. So we're going to talk about that quite a bit and provide a little bit of background on statistics and quantitative analysis that can help understand the importance of certain types of failure rates. The next module after this will be a workshop on scenario definition and common mode failures. Then we're going to get into some of the more detailed and for people who have safety instrumented systems and have to do safety integrity level calculations. There's a variety of techniques. The most commonly applied one is layer protection analysis, or LOPA. I want to talk about that and how that interfaces with HAZOP studies. I want to pull it all together in a workshop in Module 8, talk about revalidations. One of the things that really tends to trip people up is when they do a HAZOP study, they're not looking ahead to make it easy to update it in 5 years. And then, of course, updating a HAZOP study 5 years later, it can be a bit of an art. There's probably a different crew, different team that was doing it 5 years previously, different information. How do you go ahead and bring everything up to date? All those are important issues for HAZOP study revalidation. Other key topics for Module 10 will be another team facilitation workshop. Going to give you a little bit of background on some software that we'll be using for that workshop today. Module 11, human error, facility siting, and also doing design basis cause-by-cause HAZOP studies. Those will be Module 11. Module 12, we're going to talk about a lot of common configurations, how to easily handle them, and also look at multiple consequence categories. Okay, so what I want to do, I need to go and reset the computer real quick, and we're going to get on to Module 5. Just like that. All right, so your handout materials. By the way, we've got a lot of computer equipment going on around here. So it's actually real pleasing that things seem to work pretty smoothly, typically. So anyhow, we're on Module 5A, and I'd like to focus on facilitation tips and a little bit of background on a software package we're going to be using for the workshops. We already talked about what we've been doing in previous modules. So the key topics for today, we're going to talk about things like room setup, the mechanics of actually doing the HAZOP study, using LCD projectors effectively, risk ranking, how to effectively use a scribe or recorder, team size, progress, how to maintain focus when you're doing a HAZOP study. How do you balance issues such as overall cost and quality for the HAZOP study? Very few of us have unlimited budgets to do whatever we want to in this arena, so you want to be creative in terms of making sure it stays focused, and you deal with the issues that are most important for maintaining the safety and integrity of your plant site. The importance of facilitator preparation, using session time effectively, and then a few pointers on when you're using software packages. So let's get a reminder on what we're trying to do. Okay, all of this is being done to help identify potential weaknesses in the system and identify outliers, things that need to be improved to make your plant safer and eliminate any weaknesses that can end up hurting somebody or causing some sort of environmental impact. That's what this is all about. HAZOP studies are the mechanism to do that. The design information that you've got with P&IDs basically tells you how the system is supposed to work. Hazard and operability studies are looking at it in a very different way to identify how things can fail or not work, and that's what it's all about. That's how we uncover potential weaknesses. So you use a deviation matrix. We've gone over this in previous modules for combining guide words and parameters to come up with overall process deviations that can help brainstorm and identify potential failures, which you then cycle through on a case-by-case basis to develop the scenarios, identify if they're important, identify if there are any weaknesses, and make any recommendations or action items for improvement. That's where the rubber meets the road. That's what you're trying to do, is uncover actions that need to be taken care of. That's what the HAZOP study is all about, and it's usually documented in a tabular form that clearly lays out the scenario. And as we talked about the details of the scenario in the last module, we did identify a lot of ways and a lot of things that need to go into those scenarios to make sure that they're useful for evaluation and for taking corrective actions. So that's what we're trying to do. We're trying to get to those, to identify those weaknesses. All the other stuff that goes on in the HAZOP study should be designed to help the team uncover those weaknesses. So that's where good facilitation comes into play. And let's talk about a couple of tips for that. First of all, let's talk about room setup. This is a standard U-shape for room setup. Basically, that's how we've got our training center over here set up. And the idea is you don't want to use a classroom style where you've got one person in the front, and then you've got a whole bunch of chairs that are just facing the front. The team has to interact together, and this kind of setup allows that to happen. The blue circles on the left are, and it doesn't matter whether it's left or right, but basically that's where I usually put the facilitator and the scribe. The facilitator being in the front, closest to the screen, where the material is being projected. We'll talk a little bit more about that, but that allows the facilitator to easily get up there, get the team's attention, move around, get to the drawings. So basically you want to be in a very mobile, if you're a facilitator, you want to be very mobile. Right next to you, you want the scribe or the recorder, the person that you can help, it's going to work with you to help guide the team and help control the team. You want them right there. You want to be able to point to things on drawings, point to things on the screen, have very quiet sidebar conversations to keep things moving so you can get the scribe and the recorder to help you effectively get the job done while the team is having their discussion. The team, they do need to talk about things. That's why you want a U-shaped room. They need to face each other. You want to maximize participation. In terms of maximizing participation, usually I like to put the most vocal person, the person who's going to contribute the most, at the opposite end of the room. That helps my interaction, if I'm facilitating with that individual, means that you're going to draw all the individuals in the room into the discussion. In a similar way, if you want to kind of, if there's a lot of sidebar conversations, I've had HAZOP studies on systems that are so contentious and so much of an interest from a project perspective. I've had over 30 people in the room. And in a situation like that, there's no way you can draw everybody into the conversation. You never get anything done. So in a situation like that, you might want to bring some of the more vocal people or more useful people closer to you, because because there's too many people in there with too many different agendas. So as a facilitator, you'll want to go ahead and organize the room to get the job done, focused on the project objectives. In terms of the things you want to have, you want to make sure that you have large copies, as well as the 11 by 17 copies that you hand out to everybody for their personal use and personal notes. You want to have large P&IDs and process flow diagrams mounted on the wall so that you can point to things, you can highlight nodes, you can, again, get people's attention and keep them focused. The LCD projector, another good mechanism for keeping people focused. If you're not using a projector or some mechanism to get their attention in a certain area, they tend to wander. They're thinking about something that may be totally different from what you're trying to get them to derive in terms of the HAZOP study scenario. So having a projector where you can go up to the screen, point at things, where you can get them to focus their eyes in a certain area, and on the scenario you're working on, that can be very helpful. We'll talk more about that in a few minutes. A projection screen, of course, computers for the scribe. They're going to be taking the session notes. They'll probably be using one of the several HAZOP study software packages to take those notes. And it's usually those notes that are projected, but having the design information in a PDF format on the computer can also mean that if you want to talk about certain design details, those can be displayed and you can bring the team's attention on that. For the facilitator, I always carry my own computer where I'm taking some notes, maybe some things I want to bring up later and I don't want to forget. There's sometimes the team doesn't have all the information, so you might want to make a parking lot or keep a parking lot of action items to come back to. Not things that need to get worked on in the field or are going to happen months later, but things that you'd reasonably expect to be finished during the course of the HAZOP study. And also, while the team's focusing on the problem at hand, I may be looking ahead, doing some research, taking an HTML copy of the notes from the last break, basically the cumulative notes for the last break, and finding information, making sure we're not duplicating stuff, and planning ahead to make sure the team stays guided and on track with what you want to accomplish. We talked about the LCD projector, the large copies of the P&IDs and PFDs on the wall. During the breaks, in terms of getting the thing done, you want to make sure that each note is highlighted. If you're going to give them a break and going to start on something else, that's usually when I take a few minutes to go up to the wall and highlight the next node. It'll kind of bring people back into the room kind of to watch you, and also it's a good way to kind of refresh yourself of the design before you move on to the next area. And I'll talk a little bit more about facilitator preparation shortly. And you also, before you start a certain node, you're going to review what the node boundaries are, what the intention is, and also the key process parameters. Something that I didn't mention that's actually becoming more and more useful, just like this current webinar allows you to tune in very easily from whatever location you're at and get some key information. We've been very successful at conducting HAZOP studies, short ones and also at length, using a WebEx or GoToMeeting, that kind of interface. Very effective. Well, it's not quite as effective as being there, but given the fact that you can schedule people more easily, you don't have travel concerns. If you're getting people coming in from different areas of the world to participate in your team, it can really get a lot of work done very quickly and short-circuit the time on your project to getting the HAZOP going, getting the information you need, and getting any weaknesses that you've uncovered back into your design. Very effective tool. I just encourage you, if you have any questions on those kind of things about the specific logistics or what works and doesn't work, give me a call. I probably should add a module for that too. Also for mechanics, you want to make sure that I like to predefine key causes. A lot of the basics, as part of my preparation, I'll review the design and populate the software with a lot of the causes, things that I want to make sure come up. And of course, they're the more basic elements. So I can make sure the basic stuff gets done. It allows us to pace the team a little bit better. And the team can focus on identifying maybe the less subtle, maybe the more subtle type of causes that may not be obvious from the facilitator or somebody from the outside looking at the design. Also, when I'm facilitating, continuous reminders. I want to make sure that the team is always thinking about other potential hazard scenarios. Even if I pre-populated the HAZOP study with a lot of causes, you really want to get them to think outside the box. Human factors, there's only so much you can do in a conference room when you're doing the HAZOP study. The operator, the field personnel, the ones who know the physical layout of the unit, they're going to constantly be thinking about ways that things can, configurations that can cause people to get hurt, configurations that can cause people to make a bad decision, or configurations in the field that can impede emergency response. A lot of human factors issues, and I constantly remind them that that's a very important element of their responsibility, the reason why they're on the team. Facility siting is another one that's very much associated with physical layout, so I always want the team to be thinking about those kind of things. Reviewing general issues for each node. There's usually a list of things that I want them to be thinking about. I'll provide periodic reminders of that. And also, at the conclusion of each node, I'll do a completeness check. Basically, I'll have a set of drawings that I haven't pre-noted and I haven't put my personal notes on, and I'll basically check off that we've covered the key components and basically highlight the node at that time, just as a completeness check and to make sure that we've done a good job. I talked a little bit about LCD projectors and use, and let's make sure we picked up all the things. Again, the key display is usually team notes, and engineering drawings are really good to have as a backup. One of the things to keep in mind is that you're going to be doing cryptic notes during the session. I always tell the team, you know, if there's something that's wrong or can't be easily figured out later, especially tag numbers, making sure the equipment identification numbers are correct, that's something you definitely want to pick up during a HAZOP study. Beyond that, it's more wordsmithing, and it can really bog the team down, and you really don't want to allow for that. I also tell the team that, you know, don't worry, you're going to get a copy of this to look at, to review. That's the nice thing about doing everything on the computer. It's easily updated later on. And if you do a complete job laying out the scenario, it's really easy to figure out things later on and make any appropriate updates, as well as using it for MOC and revalidations later on too. I'm standing or moving around most of the day. If everybody's sitting down, it gets a little more monotonous than it needs to be. And by moving around, it tends to draw people's attention and focus. And maintaining control of the group is important. If you've got an overzealous team member who's spending a little too much time jumping up to get the team's attention, that can be a little distracting. If necessary, you might want to have a sidebar conversation with the individual outside of the conference room. LCD again, the LCD projector, the advantages are it reduces the amount of post-session review needs, but you really got to maintain control of the group and prevent them from wordsmithing it. Risk ranking, basically a lot of times it's hard to converge a team on that. I like to go ahead and provide them with a couple of options. Rather than just showing them a risk ranking matrix and telling them, oh, what's the risk ranking, tends to make it a little bit open-ended. Understanding the scenario, I'll usually give them an idea of, okay guys, is it a likelihood of a 3 or a 4, to get them to focus a little bit and make it a little bit easy for them to choose, and also makes it short circuits all their thinking, because they're usually thinking about does it precipitate an action item or not. Combining scenarios, or especially combining causes, can streamline the risk ranking effort. You know, there's usually no reason to have a cause for a valve mechanically failing open, then another cause for a controller causing the valve to open. These are things that can often be combined, as well as the bypass. Pulling all those together means that you're going to think about it once, do a good job at one point, and not be risk ranking all those little details. I mentioned the facilitator suggestions, and also it's good for a facilitator to be keeping in mind, and also when reviewing the document later, to make sure there's consistency between the different consequence severities. If you've got one scenario that is an overpressure of a vessel and the team ranked it as a severity B, and then 15 minutes later, the same vessel overpressurization is ranked as a severity D, there's an inconsistency problem. It's either they didn't understand, or perhaps they're thinking of a different scenario and we didn't quite capture all the right details in the HAZOP study. So either way, that's something you want to resolve. And the risk ranking helps you do that. Scribe advantages, some people call it a scribe, some people call it a recorder. It's the person that's sitting there taking notes while the team discussion is going on. the key thing is team efficiency. By having the scribe do that, I have facilitated and scribed at the same time. It's doable, and if you're traveling long distances, maybe it's a reasonable balance of travel costs versus additional team time, but it does increase the team time, and you've got to find whatever balance works best for your organization and your application in terms of applying a scribe and the streamlined team time where you've got a whole bunch of people that are having their time eaten up, which can be expensive on the session, versus the additional cost of actually doing a scribe and having that additional person participate. In most cases, it makes a lot of sense to have a scribe or recorder doing it, and also helps the facilitator focus and keep the team progressing rather than get bogged down in the documentation or typing. Scribe training, preparation, and qualifications are critical. Just grabbing the closest typist and throwing them on the team usually isn't very effective. They've got to know the software. They should understand the design so that they're picking up and listening to what the team has to say and is properly capturing the key elements and the important stuff. Also, if the scribe's not trained and not ready to go, the facilitator's getting bogged down. They're helping to help the scribe, and anytime you are not pushing the team for to accomplish their objectives, they'll get stuck in sidebar conversations. They'll start wordsmithing the documents on the screen, or they'll get sidetracked on completely different issues or start talking about politics. No matter how you slice it, reining them back in and getting them back on track can be really tough. So having a well-trained scribe and a team that works together, the scribe and the facilitator, really important. And of course, the scribe has to let the facilitator have the final say. The facilitator is the primary person responsible for the quality of the HAZOP and documentation, and they're the ones who have to have the final words in what goes in the document. Team size, I mentioned a HAZOP study with 30 people. You don't want to do that. It's very difficult to control, and it may sound very attractive to have all these people with all these different insights, but the fact is it just raises a lot of discussions about things that may not be a very high priority, perhaps issues to them, but not necessarily issues or things that can help the team focus and accomplish the objective of identifying potential design weaknesses. As needed, you can bring in other people. You can start with a reasonable team that you can control, and if you need specific expertise, they can be brought in. With respect to progress and focus, keep that team moving. If you're on a good topic, don't just break because it's a certain time. Find a good break point. If they need to stay a little bit later to accomplish a few things, great, let's do that. They'll be proud of their accomplishments, and you can give them a break later on during the HAZOP. Anything that's not critical for the PHA, table is an action item. Table is a parking lot item. Anything to get people from wasting their time to discuss stuff that's not directly related to getting the HAZOP study done. Again, use that parking lot. I use a flip chart quite a bit. If it's so that the entire team can see what sort of things need to be followed up on, and always put a person's name on it. If you want something done by the end of the HAZOP study, and if it doesn't have a name on it, chances are with the HAZOP study and their normal duties, their normal job duties, it's not going to get done unless a specific individual is assigned. And highlighted at the bottom, and something that you may want to continuously remind the team to do, is avoid designing solutions during the PHA. And I mentioned overall cost and quality. In fact, I think I kind of took care of this. When you're balancing the team size and who's involved, the scribe, yes, it costs a little bit extra to have that person assigned to it, but for that small incremental cost, you can get a big boost in team efficiency, the quality of the HAZOP study, and the facilitator can get some assistance in documentation, all of which can maybe lower the overall net costs of the project, and it provides an additional individual to help prepare and make sure that all the process safety information and background information is available for the team. Facilitator preparation I briefly mentioned earlier, but the facilitator isn't the primary person responsible. They're usually an engineer, and they're not primarily responsible for the providing the process engineering expertise, but they ought to have reviewed the drawings and have enough background information to properly facilitate know when the team's reached a conclusion, and it's critical for maintaining the progress of the team that the facilitator is properly prepared. Also, if you have a little background, if the facilitator has a little background information and can provide that, as well as guiding the team effectively, throwing a couple of insights or experience-based or similar situations that have been encountered for other types of HAZOP studies can often be very much welcomed by the team. In terms of noting, the preparation of the facilitator, defining the notes before the session, can provide a good framework to make sure that the job gets done properly, that you don't miss stuff, and there's a lot of cases, there's a lot of an art to defining nodes to make sure that everything fits together, it can be evaluated efficiently, and so you can find things later for that 5-year revalidation. And I mentioned earlier when we were talking about nodes that large noding to the point where it captures related information is usually the most effective. Also for facilitator preparation, I mentioned defining the causes up front. It provides structure. You can set it up in a very consistent manner rather than just random brainstorming of causes, so things can be found later, and if you're updating it for management change or for revalidation, it can be much more effective. It also makes sure that the job is thorough, and a lot of times, in fact, I think probably the reason when I first started this many years ago of why I started doing this is when a team started bouncing around and talking about what if the valve fails open as a more flow issue, and then when they talked about high temperature issue, oh, what if the valve fails open? They spent a lot of time discussing where, under what process deviation a failure would be, and if you've already got a structure that works, and if the team says, well, wait a second, what about this high temperature issue? You can say, we've already got it logged as something that's a causal event that we're going to be looking at, and it immediately curtails the discussion to get them back on track so they can be thinking of new scenarios. But it doesn't want to stifle their thinking about it. You want to make sure that the PHA team knows that they've got a lot of opportunity for defining those causes. I already talked about combining causes with identical consequences. That's a big time saver. It helps the team focus, and it gets a more thorough job done in most cases. The last bullet on the page, and I want you to be really careful with this, if you've got similar portions of systems, it's really tempting to just copy from one area, from one node, and put it into another node. I'd encourage it as long as you've taken a look at it up front and verified that the function is actually the same. Copying it and not letting the team think about it or not encouraging them to think about it is not a good idea. Copying it to save time and have the simple stuff already done is a good idea. Also, there's going to be some dead time. Sometimes the team has to discuss important issues, and a good facilitator is going to know when a team really needs to take that critical mass of them being together and discuss important issues. And sometimes you can still make progress. If there's any dead time where they have to take a few minutes to talk about something, you can work with the scribe to put more causes in, clean up the documentation, or just move ahead with some scenarios. If you're well prepared and the team has already laid out the kind of consequences that can occur, you can go ahead and start populating the upcoming scenarios. And then when the team's ready and they're done with their sidebar, they can get right back on track very easily. We talked about the separate laptop. We want to avoid regressing to previous scenarios. A lot of times the team has an idea that impacts something that they've already done. The facilitator, I usually will take a note and I'll take care of it offline because if it's clearly laid out and it's just a simple augmentation of a previous one, you don't want to spend a lot of time going back and forth. It really burns team time. When you're doing breaks, make sure you clearly specify the break length before they leave. A lot of people like to take long breaks. It's also really good to know how to find the key people in the study. When you get a team going, a lot of times you won't know them at first if you're a facilitator coming from the outside, but pretty soon you're going to know who the person is with the most knowledge, the most background, and who's going to be the biggest contributor. If nothing else, know how to locate that individual, those individuals, and also the process engineer and operator. Get their cell phones, know where their office is, track them down if need be, and get them back after that break. If they're really good people, chances are other people are going to be after them too. So as soon as they go out for their little break for the HAZOP study, they may get sucked into something else very easily. We talked about team participation and how to lay out the room. The key thing is avoid discussing the same scenario in multiple locations. If that example I provided before, you've got a valve opening up that can cause more flow, but also increases temperature, only document it in one location. The HAZOP study isn't, the way you set up the process deviations, it's not to identify every deviation. That's merely meant to precipitate thoughts of specific causal events to lay out specific scenarios. So once you've got that specific scenario defined, one place is more than adequate. And I've done a lot of revalidations where somebody has done a sloppy job in the original HAZOP study, and you get a lot of different, seemingly different scenarios that when you really dig down, it's really the same causal event that was documented multiple times, just documented very poorly. So doing a scenario once, doing it completely, and taking all the tips that we've been providing in terms of documentation completeness, very important. Bulletizing safeguards and consequences can also help focus that. And also, as a facilitator, knowing when to stop the discussion. If it's going around in circles and you're not going to get any additional insights, stop it. If they're just talking about a minor operational issue that's a headache, document that it's an operational issue only and move on. If they're talking about some issue that's out in the grass, document that there's no hazards identified, because there's probably something more important that they should be talking about, and you don't want to have a lot of time spent on the team, by the team talking about minor operational issues, and then the time that you need to have them, where they need to be talking about more important issues, gets compromised. Okay, and also, unless it's driven by risk ranking, everything doesn't need to be improved. The fact is that if the team is in good conscience, has identified no weaknesses, it's okay to document that, hey, we thought about this other design option, but it's really not driven by weakness or by risk ranking, and it's really not necessary. That's actually as useful as identifying weaknesses where design items need to be or design improvements need to be made. If the team has really thought about it and identified that it's okay as is, and then you document in the comments column that something really wasn't necessary, that means you can stop a lot of people from having to spend time rethinking it over and over and over again outside the HAZOP study, and they can be thinking about more important things in terms of design and operations improvements that really do have a nice impact on safety. And also, a specific causal event may have a bunch of consequences, but you really want to focus on the ones that are most important. That valve failing open that we talked about earlier, it could have a severe safety impact and also a bunch of other problems with respect to business interruptions, replacing equipment, and whatever. Well, you know what? Go ahead and list those if the team is discussing them, but focus on the overpressure event, focus on the thing that's going to be a safety impact and is driving your risk ranking, and that's the part that uncovers the weaknesses. You don't necessarily need to break it into categories for every consequence. And we'll be talking a lot more about that in Module 12. With respect to recommendations, make sure they're assigned to specific individuals. When they're generalized, a lot of times at an operating facility, they get deprioritized and don't get worked on for years and either cause safety problems or issues with respect to regulatory problems. Excuse me. Documentation should be self-standing and interpretable if it's disconnected from the supporting worksheets. If you've got a recommendation, it's going to get plucked out, put on somebody else's desk. It needs to be complete with respect to why it needs to be done and what needs to be done very specifically. Don't repeat recommendations for emphasis. I see this all the time when we pick up somebody else's HAZOP study to do a revalidation. You see the same recommendation over and over and over again. That doesn't help anybody. All it does is make additional action items on the tag list and make it look so big that nobody wants to work on it. A good way of addressing this is do a recommendation once, the most important place if you can, but at least do it once, and then in the other scenarios that reinforce the need for that recommendation, just make a cross-reference note rather than an additional action item. Also, a recommendation closure, make sure it's set up and that people at the plant site can get to them and close them in time. Other ways to keep to make the HAZOP more valuable is and it's in terms of soft alarms and how to address them. Rather than make recommendations over and over and over again for something that's done in a few minutes at the control console, go ahead and mark up the P&ID master copy, and the masters are usually assigned to the process engineer, and just go ahead and mark it up, make the change that they're going to implement, and just note in the HAZOP study that during the course of the HAZOP study that you made this little change. That'll keep your action item list smaller so that the important stuff actually does get worked on. Also, using the comments column. Rather than putting a lot of clutter in another area, if there's ancillary information like maximum blocked and discharge pressures of pumps or other design features, the comments column is a good place to log that. Also, if you're referencing operating procedures, I see that over and over again, and I do it too. You'll talk to the team about operating procedures and mention it as a safeguard. Well, at least occasionally, ask them which procedure, give me a procedure number, or show me, so that they're not just talking about operational practices of what they do, but they're talking about specific written procedures that they must follow. Also, time limits. It's fair to tell the team that if they can't figure out a consequence of an event in 5 minutes, maybe it's a complicated sequence of scenarios, but if they can't, or sequence of activities, if they can't figure out in 5 minutes, it's okay to tag it as an action item. Hey, the team did not understand the phenomenology associated with this, didn't understand the consequences, and make an action item for follow-up either during the HAZOP study or the parking lot. Also, risk ranking. If they're going around in circles because it's a contentious issue, it's okay to leave it unranked and put a recommendation for somebody to go back and maybe apply some quantitative techniques, maybe LOPA or some of the other things that are out there to actually resolve the risk ranking. And also, I can't say this enough, prolific use of equipment tag numbers. Make it as specific as possible so somebody can pick that documentation up 5 years later and go through and make sure they can understand the scenario and understand it enough to make any corrective actions necessary. Also, if an operator has to respond to multiple alarms, it's really tempting to list out all those different alarms in the safeguards column, which is okay, but it can be misleading because people look at it and go like, wow, I've got 5 safeguards. Well, they all may be console alarms, and it's still the operator that's got to take corrective action. So rather than, to avoid that, sometimes I like to group them and basically say as a single safeguard, operator response to one of the following alarms. And also, if an multiple alarms can be good, if they're contributory towards diagnosing the event and not clouding the issue. It can be bad if they're not properly prioritized and just have so many different things going on that the operator has trouble diagnosing what's happening and taking corrective action. So any way you slice it, it's a single operator action, and also that segues into LOPA because they only give you 1 credit for operator response using 1 or multiple alarms. And also, as you're going through the PHA, verifying design pressures of equipment, piping specs, and overpressure protection items, it's very useful. I like to do that kind of at the end of each node, is go back through and just verbally look at the design pressure of the vessel, verify it's protected by the relief, correlated to the set points, and ask about the sizing if it hasn't already come up in the various HAZOP study scenarios for that node. It's valuable. And no matter how many times people look at certain designs, you're always going to find something new. And I've gone through a lot of operating facilities where a simple double check of the design pressures and relief valve settings will yield deficiencies where the relief valve is the set pressure is too high, or it's just not sized properly, or it can be isolated from the device that it's trying to protect. And those are very useful things to do. And also, if you've got a long relief flow path, look for isolation points and verify that the equipment that's supposed to be protected is actually protected. All right, what I'd like to do, we're going to be having some workshops using some software and doing things interactively. I just want to briefly introduce this. This will be the software package that's going to be used, PHA+. When we go through that, we want to, it'll be tab-based. There'll be tabs for identifying worksheets, recommendations, node level or project level information. There's a lot of additional features and pull downs just like standard software. And also there'll be a navigation pane on the left. so we can see where we're at in the HAZOP study, or basically what node we're at. If you're on the node screen, a lot of opportunities to add and delete and also edit the various features of the node. On the deviation area, there's pull downs for a lot of the standard process deviations that need to be looked at, and then adding them to build your deviation list that you then build your causes when you're going through the different worksheets. There's tools feature for spell checking, risk matrix maintenance, and also for defining character sizes. On the worksheet area, we're going to be interacting with this, grouping the causes, consequences, and safeguards into one area so that we can focus on the scenario, pull downs for risk ranking, and also various navigation panes and places to put in tracking numbers, and also associating multiple recommendations with a specific scenario. So those are the kind of things that right before the workshop, you want to reference back to this so you know what you're looking at as we go through it. What I'd like to do is take a few minutes, and it's a little tough to do a quiz on a webinar, but what I want to do is use our standard quiz like this to talk about some of the key points that we've been discussing. Basically, true or false, larger PHA groups can increase facilitation challenges. Well, that's certainly true. With larger groups, you really got to be on your toes as a facilitator to keep it focused. Additional expertise is there, but as I mentioned before, you could also burn a lot of time with sidebar conversations and people bringing in other issues. Should detailed design issues be addressed during a HAZOP study? No, the HAZOP study is not to do the detailed design. It's really to go out and flush out any potential weaknesses. And is all you need for a scribe or recorder a fast typist? No. You want somebody who's trained, can work with the facilitator, understands a little bit of the process. Usually a newer process engineer is a good choice for a scribe. They can pick up on what the team's saying, capture it properly, and it's a really good match for keeping that team moving. All right, so can inaccurate or incomplete process safety information significantly impact the duration of the HAZOP study? Absolutely. So it's false that it's not likely to significantly impact the duration of the HAZOP study. When you're constantly having to rethink or ask questions about missing design information, and I've done HAZOP studies where I've got the P&IDs, I'm properly prepared, I understand what's on the P&IDs, and then I start asking questions about what can go wrong, and I'm talking to the group and I'm getting these blank stares at me, and then after about 5 or 10 minutes they say, oh, we removed that equipment, or oh, there's an extra pump there, or it can be totally different from what's on that P&ID. So you can waste a lot of time with inaccurate P&IDs. It's always a good idea before the HAZOP study to go back through and properly field verify and update the P&IDs so the team can focus and work efficiently. HAZOP study facilitators don't really need to prepare because they simply ask questions. Absolutely false. Now that is the classic way of doing things, and yes, the facilitator's primary job is moving the team, but the fact is that they need to be prepared to ask the right questions and keep the team moving efficiently. Okay, so what I'm going to do, I need to take 30 seconds and retool for Module 5B, and we'll get started on some quantitative aspects. Good. All right, Nicole's way ahead of me. Okay, so what I want to do is the focus of this, in fact, I started developing this really to just talk about double jeopardy. And then I realized that to do it properly, I needed to provide a little bit of background, and I thought it might be pretty useful. In fact, it is useful when you're facilitating HAZOP studies to really understand basic issues about equipment failures, how things go wrong at a facility, and how that fits into defining the likelihood of a scenario. So I want to provide a little bit of background on quantitative issues and also segue right into how that factors into something that's often done improperly, which is applying a double jeopardy argument for eliminating discussions on scenarios. Okay, so the key things I'd like to do is talk about the basics of quantitative techniques, probability distributions, component life cycles, and different types of components, repairable and monitored and unmonitored and standby, key data sources where you get equipment failure data, how LOPA fits into this. LOPA is a really good tool for doing these kind of things. We'll be learning more about that in module number 7. And then correlating the failure data that you get from all these sources to how LOPA is working, and then jump into double jeopardy. And I've also got some other background information here that I'm also going to talk about and provide. So let's talk about some basic techniques. Now, what I'd like to do is the top figure on the right-hand side of the screen is the real world. You know, different types of equipment. You can buy the same device from the same manufacturer at the same time. One's going to last longer than the other. One's going to be problematic, the other one's not. Or at least they're going to have different levels of being problematic and different reliabilities. That's the real world. When you look at equipment, they're basically going to be mean values of how long they're going to last, when they're going to fail, and all that can be represented by normal distribution. So the real world, all equipment's a little different. Mathematically, you can represent this as a normal distribution. However, most real-world problems in terms of using HAZOP studies to flesh out potential issues and also using them for risk-based decision-making are solved with single-point estimates. And that's the little symbol down there is a lambda. That's basically a failure rate value. Or taking a mean failure rate value for a given type of equipment or population of equipment and applying that to the equipment that you're looking at in your scenario is a reasonable way and a practical way of doing 99% of what you want to do with respect to fleshing out potential problems and weaknesses and identifying design options that you want to look at. Now, it doesn't mean understanding statistics and a lot of the different distributions isn't important. There are some applications where it's very critical and you really want to do that, but again, most of them are done with single point estimates. I'd like to talk about component life cycles. In general, all equipment, electronic and mechanical, has a burn-in period or an early stage of their life where whatever manufacturing defects or anomalies were in the equipment tend to come up and you're going to get premature failure. This is typically why they have warranties on things that you purchase either for your facility or even at the local retail store, is because no matter what you do, there's going to be increased failure rates in the early stages of a product life. After that burn-in period, there's a useful period where, given a population of equipment, it's got pretty much a constant failure rate. And then you get to a point where you're long past its useful life, and a lot of people who are at facilities, you know, they've got the old turbines, the old equipment over there that may be way past its original life, but it's functioning properly, but it's going to be more problematic and going to have higher failure rates. This is typically called a bathtub curve, and basically all equipment, electronic and mechanical, has a burn-in period and a wear-in period and the wear-out period, and then this useful life is in the middle where you've got a relatively constant failure rate. It's that period that represents the majority of the life of the equipment and is the kind of thing that you typically want to look at when you're quantifying equipment failures for a HAZOP study or LOPA. Mechanically, it's the same thing. Whether mechanical or electrical, you've got the same kind of burn-in or wear-out period. Now, so the useful life of the component has pretty much a constant failure rate that's typically represented by MTTF, or mean time to failure. That's 1 over lambda, or 1 over the failure rate that's associated with that. Now, just a couple of examples. A valve randomly failing open. If you look at a lot of the guidebooks that provide data, it might be something like on the order of 1 times 10 to the minus 6 per hour. What does that mean? 1 times 10 to the minus 6 per hour is a failure rate. That's typically something that you might have represented for lambda. That means that in 1 million hours you might have that failure that you're talking about. So the mean time to failure in that case is 1 million hours. The failure rate is 1 times 10 to the minus 6 per hour. So that's how people typically tend to dialogue about these things. The burn-in period The failure rate decreases with time, as was represented on the previous curve, and it's typically characterized by a Weibull distribution. The wear-out period, failure rates increase with time, and also they can be characterized by Weibull, normal, or log normal distribution. Again, the majority of applications talk about the useful life of the component and a relatively constant failure rate. Arithmetically, and actually doing these calculations, it's a lot simpler, and it gives you the insights that you want. This is an example of, I'd like to explain what concepts of availability and unavailability. If you've got a component, this is the top half of your screen, that's operating, and then it fails, and then it's being repaired, then operating again, fails, being repaired, operating again, fails, being repaired. That's what's represented by the operating state to failed state in the top part of your screen. When you're looking at overall availability, obviously the bottom part of your screen, it's 1.0 initially, then it's averaging out all these operating versus failed state periods. And if you're looking at a given component or population of components, what that yields as you asymptotically approach infinity is a specific availability number. It's the asymptotical values or these mean values that we're really going to be talking about when we talk about equipment failure rates and probabilities of HAZOP study scenarios. Some specific definitions, some of this is pretty self-evident, and it's all provided here for background. But basically, a reliability is that that the component experiences no failures during the time of interest. Availability is the part that one we were just looking at, where you're looking at the total operating time, total time where it's operating versus divided by the total time of interest. Unavailability, which is usually the easier calculation to do, is total downtime divided by the total time of interest. Unavailability is typically what you're looking at with safeguards or safety systems that are backing up and protecting you and providing that barrier to that awful consequence when you're looking at causal events. So the initiating event, or what starts it, is typically represented in a frequency, or so many events per year. The safeguards are typically represented in terms of an unavailability. Basically, the fractional time that specific safeguard is unavailable. Because the numbers are slow, because the numbers are low, it simplifies the statistics and allows you to do the calculations a lot easier. And that's the value that you're typically using to correlate to your risk ranking matrix. Mean time to failure, we already looked at that, average time interval between failures. Mean time to repair is usually represented by MTTR, or 1 over mu, is the average time to repair a failed component. And as we defined before, the failure rate, or lambda, is the most common representation that you'll see in equipment data books. That is 1 over the mean time to failure. When you're looking again at those same monitored and repairable components, if you're looking at availability as it approaches infinity, it's essentially the mean time to failure divided by the sum of the mean time to failure plus the mean time to repair. Unavailability is the mean time to repair divided by that sum. And of course, availability and unavailability have to sum to equal 1. That's why a lot of the arithmetic works out really simply if you're looking at unavailability. A quick example for a failure rate, or lambda, of 1 times 10 to the minus 6 per hour, and a mean time to repair for 10 hours if the equipment does fail, basically you're looking at an unavailability of that equipment of 1 times 10 to the minus 5. Going back up to the top of the screen, availability is approaching 1 as your mean time to repair is very low, which makes sense. If it fails and you can bring it back up online very quickly, no matter how often it fails, you've still got a pretty good availability. Similarly, for unavailability, if mean time to repair is going up, your numerator there goes up and your unavailability gets bigger. So we were talking about monitored repairable components. When a component, if it fails, you know about it right away and you do some corrective action. An example of that would be a control valve at a plant site, where level control valve at a plant site, it goes shut and you get a level increase in the tank that's going to be quickly noticed by the operator. That's a monitored type situation. In that kind of situation, you can apply the equations that we just talked about. Another common type situation that tends to throw people is an unmonitored case, even if it's repairable. There's a lot of equipment that's out there that could be in a failed state, and you just don't know about it. It could be a control valve that doesn't get used very often. Maybe it's a pressure regulating valve going to your flare off of some sort of head tank, and that never opens up because your tank is always slightly below its set pressure, and because it doesn't open up, you don't know if it's going to. It's essentially unmonitored. For a situation like a relief valve, that's essentially the same thing. It can be sitting there for years at a time without functioning, so unless you're pulling it off to test it, calibrate it, or to replace it, you really don't know if it's functioning. So for situations like that, and this occurs for a lot of safeguards, your basic component unavailability is the mean time of unavailability divided by the mean time of interest. The mean time of interest, say for a relief valve, if you're replacing it every 5 years or calibrating it every 5 years, is the time between tests, and that's represented by tau. Your mean time of unavailability is very simply, because the failure rate function is lambda times the time that's associated with that, it's the integral from 0 to tau of the failure function times dt. Very simple integration from high school calculus shows you that the mean time of unavailability is lambda tau squared over 2, and when you carry through the in the top bullet item there, basically unavailability is equal to lambda tau over 2. This 1/2 lambda tau function is one of the most important equations that you'll have to remember for equipment reliability associated with the kind of scenarios you look at for quantitative risk assessment, for LOPA, and also for HAZOP studies. It characterizes a very large population of devices that don't operate regularly, that may fail and go unnoticed. And it's also pretty intuitive, too. You're really looking at the half of the time of interest times its failure rate. So basically, if something's out there sitting in a standby state or basically unmonitored, it could have failed right after you install it, and you won't know for 5 years or until it's challenged. It could fail at the 5-year period. So that average of when it could be unavailable is basically 1/2 lambda t. Real easy. For standby components, again, looking at relief valves or that pressure control valve that I spoke about, you've got a lot of, basically they're always in standby. They're rarely operating, hopefully, unless you're testing it. So it basically cycles through various test modes. You may have to use it, various test modes, and then it could fail in the standby state and not knowing it, and that's what this chart is representing, all these different states and the fact that it can be failed and you're not knowing it. Now, one of the nice things is modern electronics. There's a lot of smart sensors and a lot of fault-tolerant devices out there that can really help you identify if something's happened with the equipment, especially electronics. And those have been really helpful for lowering the incidence of undetected failures and making sure that you maintain overall availability, minimizing overall unavailability of key safety equipment. For standby components, a couple of things we need to keep in mind. I talked about what really drives that. What usually drives that is the 1/2 lambda t. For hardware failures such as a relief valve, these are all unrevealed failures. An unrevealed failure can be a function of time, as in the first sub-bullet, unrevealed failures being 1/2 lambda in the standby mode, that's what lambda s is, times tau. These unrevealed failures, if you've got a standby failure rate or lambda sub s given to you, you can identify the unavailability of that equipment with 1/2 lambda tau. Also, equipment reliability data books, especially for relief valves, will often have a failure to start on demand or failure to open on demand. If that's provided directly to you, that's basically the one you'd use. So typically when you're looking at the unavailability due to hardware failures for standby equipment, it's either given to you on a per hour basis, in which case you'd use the first equation, or it's given to you on a demand basis, in which case you just use it directly as your probability of failure on demand for your layer protection analysis. The second bullet there, unavailability due to test, that's the mu that we talked about earlier. It's basically the test time over the total time of interest, similar to maintenance. For repair, it's basically the mean time to repair over the sum of the mean time to failure plus the mean time to repair. Now, for most equipment with low failure rates, if your lambda is sufficiently small, most of these, obviously your total unavailability is the sum of all four, but it's usually driven by Q1, or that unavailability due to hardware failure, or basically a covert failure that may have occurred during a case when the equipment's on standby. Okay, let's talk about data sources. I mentioned that there are data books out there. I've listed some of the key ones. The Center for Chemical Process Safety LOPA guidebook has some basic information. CCPS also has a more detailed taxonomy of guidelines for process equipment reliability data. Offshore reliability data, ORADA, a lot of good information compiled from the offshore industry, especially in the North Sea. Rome Air Force Base has a reliability analysis center that keeps track of information. Rome Air Force Base also has an NPRD that keeps track of non-electronic parts. IEEE Standard 500 is good. SYNTAP is pretty good, and you've also got the Instrument Engineer's Handbook. All these are important data sources, and in your handout package, I've provided these references at the end. To summarize, a layer of protection analysis has a lot of the key information that you're going to use on a real regular basis when you're doing a HAZOP study, LOPA, or even quantitative risk assessment. Things like instrument loop failures, regulator failures, things that can lead to an initiating event. Also human error. They've kind of characterized a lot of the key human errors that are out there. For the safety features, or your independent protection layers, or how they're referred to for LOPA, control systems working, relief valves, rupture discs, a lot of those things are listed out here, and I've just repeated them for convenience. Every LOPA is different. These are just representative LOPA values, but notice one thing. They're all pretty much one significant figure. When you're trying to apply a practical approach, just as you use single point estimates, as I mentioned during the first slide of this module, you're also going to use simplified amounts because the accuracy of the information isn't there. When you're applying data that's not yours, that's not for your specific equipment, and usually because for reliable equipment, you don't have a lot of failure rate data, there's always differences in terms of how it's applied. The population that generated the data may have different manufacturers, different operating conditions, clean or dirty service. There can be a lot of differences. And also reporting. Have they reported all the failures? Have they accurately binned what types of failures they are? All those lead to uncertainties into the accuracy of the information as it applies to your equipment and your plant site. So one significant figure is even really good in terms of accuracy as it applies to you. But using these types of values, doing these approaches is more of a screening approach to separate the really important stuff from the not very important stuff. And we're going to be talking more about that when we talk about double jeopardy in a few minutes. But what I do want to do is we have gone back and looked at how these simplified LOPA values correlate to a lot of the other data that's out there. And just from a representative sampling, it's usually pretty good. Even though LOPA is designed to be simplified and over predict the equipment failures, it's not all that radically different from a lot of the other equipment data that's out there. Just a quick snapshot from Lee's Loss Prevention book. For relief valves, they have a lambda in standby, or a failure rate when it's in a standby mode and not being used, of 5 × 10⁻⁷ per hour. That's basically 1 in 2 million hours would be an expected failure. Now, if you're replacing or calibrating or reconditioning that relief valve in a 5-year period, basically 5 years, you're looking at 24 hours times 365 days per year times 5 years. For 43,800 hours, and you carry through the 1/2 lambda T calculation, you're basically looking at 0.011 per demand. All right? If you look at the LOPA data, it's 0.01 per demand. Pretty much spot on. You're looking at a control valve from Lee's, 3 × 10⁻⁵ per hour over a period of a year where it's operating so it could fail at any time, which would basically be lambda T, or your failure rate by the time of the time interval. It yields 0.26 per year. Well, LOPA data has 0.1 per year. pretty darn close when it comes to all the statistical uncertainties that are associated with this. So whether you're using very simplified LOPA data or whether you're going back to a lot of these handbooks, the differences aren't dramatic. And as I mentioned in our first slide, using single point estimates and general values for these are going to lead you down the path of identifying, is your scenario extremely important, highly likely, or very unlikely to occur? It will get the job done. And most importantly, in fact, one of the first papers I did on this topic in 1985 at a Canadian Chemical Society conference, one of the questions from the audience is, well, there's so many statistical inaccuracies in the data. Why use it at all? Why do this? Well, the fact is that, yeah, there's a lot of uncertainties with respect to the data, and certainly uncertainties in terms of how you apply the data to your plant site. The fact is, on a relative basis, it's certainly going to separate the ones that are very likely from the very unlikely. And you know what? For the job you're trying to do for the HAZOP study and LOPA for identifying weaknesses, that'll get the job done, and the relative values are just fine. So let's talk specifically, now that we've got a little bit of background in some of how failure rates get calculated, let's talk about double jeopardy. First of all, the classic double jeopardy approach is to ignore two unrelated failures occurring at the exact same time. And there's a lot of merit to that. In fact, the approach originated from relief valve sizing calculations and the guidance documents associated with that. But when you apply it to the HAZOP study, because the HAZOP study is already looking at combinations of failures, it can be misleading and misused, and it can lead to confusion. So let's talk about when to apply it and when not to apply it. A good way to think about this, and this is something I encourage every HAZOP facilitator to do, is really understand probabilities, understand statistics, understand equipment failures, what the uncertainties are, and not to calculate all this stuff, but to understand it so you can guide the team and you know if a team needs to be looking at something, and that's what your job is all about. So let's look at two examples and whether double jeopardy applies. First example is two normally operating control valves. Now they're both normally operating, so that goes into the monitored component that we talked about earlier. A failure would be noticed. Let's assume the HAZOP scenario cause is both valves simultaneously being in a failed state. Well, your frequency of that occurrence would be the failure of valve 1 during a 1-year period, if you're looking at an annual frequency, times the conditional probability that valve 2 has also failed during the time that 1 has failed and being repaired. Assuming a 48-hour repair period, valve 2 has to fail during that 48-hour period where valve 1 is being repaired. So to calculate the frequency, you're basically looking at lambda 1 times the time for a year. That tells you the likelihood that valve 1 has failed and is in a repair mode. And you multiply that by the probability of failure during that repair mode of valve 2. So it's lambda 2 times the mean time to repair for valve number 1. Putting in the same numbers that we just used from the Lee's handbook of 3 times 10 to the minus 5th per hour for an operating valve failure, and of course there's 8760 hours per year. And then if you're looking at a mean time to repair of 48 hours, it comes basically out to a frequency of 4 times 10 to the minus 4th per year for this particular occurrence. Now, that doesn't tell you, I want to compare that to something else, but is this a double jeopardy issue? Well, you know what, it does fit the definition. Should you go ahead and use a double jeopardy, call double jeopardy on it and eliminate it based on that? Well, maybe. This is certainly the case, and if the repair period really is 48 hours and they don't just leave the valve out of service because they don't have the resources to fix it and because they've got that other valve operating, oh, okay, maybe we can call double jeopardy on that and eliminate that. As long as there's no, I might ask, are there any common mode failures, control systems, or even the same maintenance person repairing both valves during turnaround? If that's the case, there may be common mode failures that can increase the conditional probability of that second valve failing. And also, are there other safeguards there? If I see this happening, it is simultaneous, it's going to have a fairly low frequency, and there's a bunch of other safeguards, I might say, okay, sure, let's call it double jeopardy, let's really not look at it. So this might be a good application for double jeopardy, and it certainly fits the definition. Let's look at one that some people try to do, and we'll see if it fits, if it makes sense or not. Another example is a normally operating control valve where you notice the failure. Basically, it's monitored. It's it's providing material to a vessel with a pressure control valve on it, kind of like what I mentioned before, and that control valve really is always closed. It rarely gets exercised. Maybe once every 3 years, the operator notices the valve opening or does something to control pressure in that vessel. Now, of course, there'll probably be relief devices on that, but we'll get to that in just a second. For these two pieces of equipment, the causal event, or what starts this, maybe challenges the relief valve, is the feed valve failing open and the pressure control valve failing to open. The frequency of that would be the failure of valve 1, the annual frequency, the failure of valve 1 during a 1-year period. That's lambda 1t, just like what we looked at before, at times the conditional probability of valve 2 failing to open. Well, valve 2 is kind of in a standby state. So you really don't know if it's working or not until you actually need it, or if you have some other mechanism for testing it. That falls into our 1/2 lambda t regime. So basically you're multiplying the frequency of valve 1 failing during a 1-year period times the conditional probability of valve 2 failing to open. Well, that conditional probability is 1/2 lambda 2 T2, where T2 is basically the 3-year period that pressure control valve is in standby. Well, you do the arithmetic with the same failure rates we just looked at, and also lambda 2, because it's a control valve that has to open to control pressure. A typical value for this, and you can actually find this in guidebooks, is about 10 times a failure rate for relief valves. You go through the arithmetic and you basically get a failure frequency of 2 times 10 to the minus 2. Well, the previous one was 4 times 10 to the minus 4. This is 2 times 10 to the minus 2. So this is essentially a factor of 50 greater. So there's a pretty big difference between these two because in this particular case, the second failure was in standby. Are they unrelated? Do they have to happen simultaneously? Correct. But in this particular case, it was a piece of standby equipment that could have been failed for a very long period of time, and you don't even know about it. So understanding the ways to calculate frequency, and also really looking through the definition of double jeopardy and applying it properly in terms of simultaneous failures, you really got to look at this and say, this is definitely not a double jeopardy case. I've had teams tell me, oh, double jeopardy, let's not look at it. When you look at this kind of thing with something in standby for this period, look at the frequencies and you look carefully at the definition, this definitely does not apply. So what do you do about that? All right, what does a facilitator do? Well, again, be careful. 9 out of 10 times, a team gets confused between these simultaneous failures for operating equipment on monitored equipment and failures of standby. So I usually totally avoid the use of the term. In fact, I cringe when somebody on the team says this, because 9 out of 10 times, probably more, it's misused. If a member of the team calls double jeopardy on you and says, I don't want to look at that, go ahead and listen to them, because they are experienced. They're your technical resource, the process engineers, the operators who really know what's going on. But carefully consider, is this really a double jeopardy application? And as necessary, apply some local calculations. It only takes a few seconds, even in your own mindset. Call a break if you have to, and take a few minutes to do a quick calc and understand it yourself, and really share that with the team if they need to understand, and really carefully look at the scenario. Okay, so that's it on double jeopardy. Some data sources provided to you for reference. And the handouts, your handouts don't have the quiz in them, but let's do a quiz. Okay, again, we're doing a webinar. We got an audience here, but we are doing a webinar, so I'd like to go ahead and just run through the answers. Most practical quantitative applications require detailed modeling of statistical distributions of equipment failure rates. True or false? True, very false. You know, single point failures, simple failure rates, one significant figure, usually more than enough for getting the information you need to make a decision. Second bullet, for a standby component, unavailability is typically represented by 1/2 lambda t. True. If you don't get anything else out of this module, please remember that and understand the concept of things failing when they're not being used that are covert failures that aren't immediately noticed. Third item, standby safety system, probability of failures on demand. That's what PFD stands for. It's a common LOPA term, are typically represented as a demand failure rate. True. You may get a lambda sub S, lambda and standby for a failure rate on a time basis, but typically you'll get a per demand failure rate. Next item, a typical value used for relief valve availability is 99%. Remember, availability plus unavailability is 1.0. The unavailability of the relief valve that we looked at a few slides ago for LOPA was 0.01. So basically, availability is 99%. That's how all this ties together. Next bullet, failure rates in the CCPS LOPA guidebook are typically much larger than values in other guidebooks. That's a trick question. The fact is they are typically larger, but not much larger. They're pretty much, there's a lot of credence to them. They're certainly conservative. They've got to be conservative and err on the high side, but it's a good simplified approach. So if you're just getting into this, don't be bashful about using these simplified values to be an asset or augment the conclusions and helping you derive conclusions for your HAZOP study. Last one, double jeopardy exclusions should be taken if there is a team member consensus. False. Don't necessarily take it. They may be totally right, but don't take it at face value. They may have done other relief valve siting calculations. They may have used the term in other contexts. They may have had a facilitator who hasn't properly briefed them, trained them, or challenged them as appropriate. And even if the entire team's in agreement, think about it independently. Think about, as a facilitator, your responsibility for understanding failure rates, how the world of statistics falls into this, and the big picture of overall loss prevention. And I think, all right, yeah, that's it that concludes Module 5B. I just want to mention we're going to open it up for question and answer in about 30 seconds. And I just wanted to go ahead and mention this was Module 5. January 19th, we're going to be doing a webinar for our next module, Module 6. And it's going to be a workshop on scenario definition and common mode failures. And I hope you'll all tune in. So anyhow, these are contact points for me. And I'd also sent out a CV in the email that went out last night. And if you have any questions right now or at a later time, you can email me, call me. And right now, we'll just go ahead and open it up wide for questions that come in the chat, on the chat for, come on in the chat area, or if you want to go ahead and phone it in, we can unmute you and we can do it audibly.
Okay, we do have one question. Would you consider a flow control valve a monitored component if during steady state system operation the valve is always open X%?
Oh, okay, that's a really good question. If it's always open at the same %, I think you need to stroke it a little bit to see if it's going to function. So I wouldn't consider it necessarily a monitored component. However, it is something that's a little bit better than no flow, but not all the way to validating its function. And in fact, that's another good question for another reason too. All these failure rates, everything else that's done, it's based on achieving the function associated with that safeguard. Now, understanding that function and devising a test program to functionally test the equipment, whether it be an alarm and you're actually testing that the sensor has been activated, or a valve that it's stroke tested that it will actually work, all those go into functional testing. So if you're not functionally testing it, then no, I would not consider it monitored. However, if you do notice on the control board that its position varies from 5% to 20% on a regular basis, I would give that a pretty high reliability of being monitored. Good question. Okay, yeah, the only other thing I want to mention is all these concepts apply throughout the process industries in wide ranges of components. The bathtub curve, the equipment failure rates, all that stuff applies universally. And also, I'd encourage you to use the LOPA numbers, even values from the RADA handbook, which are designed for the offshore world, but the fact is that the same types of equipment are often used for onshore applications, maybe even less demanding environments. So a lot of this stuff, as long as you use it carefully, can apply across a very wide range.
I wanted to know your approach to ranking the revenue loss for the causes where, say, like a compressor fails to operate and it requires like a plant shutdown.
Okay, fair enough. Yeah, that's
oh, it's unstable.
okay.
And then the second part, okay, I wanted to know how you ranked business impacts or revenue losses in addition to the hazards when you have the failure of a critical piece of equipment. For instance, say you bypass a heat exchanger, it causes no hazards, but it might cause product quality to go off spec and inability to sell the product, or a product pump fails to operate. And then also, is that a useful thing to look at in a HAZOP study, or is that more something for the design phase?
I'll answer the second part first.
Okay.
Okay. The second part is how useful is it? It's certainly worth considering. It can certainly be a driving factor. Typically, the safety impacts, if there is a large safety impact, will dominate. And as I mentioned earlier, that's something that you might want to condense into a single consequence and focus on the dominant consequence. However, if you've got something that's a marginal safety impact and a significant financial impact, they probably should both get looked at. And from a ranking perspective, usually, and if necessary, you can split them into two consequence categories. As I mentioned earlier, there are lots of good reasons to do that. When you're ranking them, typically a risk ranking will have a financial range. If you've defined a risk matrix where A through E are your consequence categories, usually each of those consequence categories will have a financial impact range associated with it. And also when it gets really hairy, and I don't want to use numbers, but when you look at those financial ranges and how most risk ranking matrices are set up, the reality is that nobody wants to say this directly, but when you cut through and look at the basis for this, you really are equating financial issues to safety impacts or financial issues to loss of human life. And when you do that, it's implicit in all the decisions we make in our daily lives, and also when you're designing facilities. It also, whenever you're factoring in financials, either downtime or other issues, it can help you balance how many improvements you want to make to the design to ameliorate that particular type of event. So it can really help you decide how much design work you want to do on it. Oh, okay, never mind. All right, well, let me thank everybody for tuning in and participating, and we'll look forward to seeing you in January.